do the unexpected. I guess if you're going to talk about art and set theory, you should start with the following quote. So, Greg Cantor's grand narrative set theory, created by him almost single-handedly in a span of about 15 years, resembles a piece of high art, more than a scientific. That's from man 10 years ago. I don't know if I agree with that, but it's an interesting. I don't even know if that's a critique of set theory or a critique of art. All right, so the universe far beyond. The mathematical story of infinity begins modestly with nothing, the empty set. So unlike, I'm going to talk just about sets. So we're going to, all the objects will be sets. So first I have to show you the sets that generalize the familiar concepts that you grew up with in mathematics. So we're talking about the ordinals, the transfinite numbers. So the empty set is the smallest ordinal, that's the number 0. Then the set whose only member is the empty set, well, that's the ordinal 1, and so forth. Abstractly, if alpha is an ordinal, then it's simply the set of all smaller ordinals. You can see that with the examples that I gave. If you have an ordinal, we tend to denote them by Greek letters alpha, you can get the next largest ordinal by just adding that ordinal. So alpha plus 1 is alpha together with alpha. And that's the next largest ordinal. Omega denotes the least infinite ordinal. And it's the set of all finite ordinals. So in every, you have a collection of ordinals, there's at least one. Oh, sorry. Whenever you have a collection of ordinals, there's always at least one. So there's going to be an ordinal that exists by the axioms, there'll be at least one, and that's omega. So we now have a layered presentation of the universe of sets. If you want to understand the universe of sets, understand it level by level. So let's look at the levels. Maybe it's not so complicated. Well, V0 is the empty set by definition. V1 is the power set of the empty set. There's only one subset of the empty set. That's the empty set. So V1 is the set whose only member is the empty set. V2 is the power set of V1. There it is. Well, wait a minute. These are just the ordinals 0, 1, and 2. Okay, but V3 has 4 elements. It's not the ordinal 3, and it's not an ordinal. All right, so things are getting a little more. What about V5? Well, it has 16 elements, and you could write them down. Okay, not so bad. V5 has 65,536 elements. It'd be hard to write them all down. But maybe it's manageable. All right, well, let's jump up a little bit. What about V sub 1,000? How many elements does it have? It has a lot. Okay, so we're not going to write that. You can't write down all the elements in V sub 1,000 in the universe, bigger than anything you can represent in the universe, according to current physics. V omega is infinite, and it's the set of all hereditarily finite sets. Omega exists as a consequence of the axioms. The transition to V omega is when you go into the infinite. Now, V omega is a familiar structure. The conception of V omega, mathematically, is just number theory. These are different incarnations of the same thing. V omega, in many ways, is much simpler. It has only one relation on it, the membership relation. And whereas in number theory, you have plus and times, and when you go back and forth between the two, you have to do some modest number theory. V omega is a more natural structure in many ways. All right, what about the axioms? So this is shaping our conception of V. The ZFC axioms are the formally specified, what one might call the founding principles for the conception of G. I'm not going to list the axioms. Now, these axioms can be augmented by additional axioms which assert the existence of very large infinite sets. And we've already seen those in some of the previous talks. Such axioms assert the existence of large cardinals. And here's some sample ones. Measurable cardinals, strong cardinals, my favorite, Woodin cardinals. And then it goes on, and the names get less and less imaginative, super strong, super compact, extendable, huge, omega huge, and the list is quite long. These are just some samples. Okay, so let's go back and look at some simple infinite sets from everyday mathematics. Well, n is a set of counting numbers. We start with 0. Z is a set of all integers. The rationals, those are ratios of integers. You have the reals. And then you might have the points of plane, R2. So those are the kinds of infinite sets that you encounter in school when you first learn mathematics. Okay, so now we want to talk about measuring the size of sets. That's cardinality. So two sets, x and y, have the same cardinality if there's a matching of the elements of the first set with the elements of the second set. Now this makes perfect sense within the universe of sets because we talk about functions. So we say the cardinality of x is equal to the cardinality of y if there's a bijection. So if you go back to those simple sets, you can see that the set of all counting numbers, 0, 1, 2, 3, dot, 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 has the same cardinality as the set where you throw out 0. What's matching at 1? A little harder. It's the cardinality of the counting numbers is the same as the cardinality of the integers, same as the cardinality of the rationals. And one can do that, it just gets a little tedious. It turns out that the cardinality of the reals, points in the line, is the same as the cardinality of the points in the plane. And that's a little more subtle and a little surprising. Somehow it feels like the plane should be bigger. If you assume the axiom of choice, which is one of the ZFC axioms, in fact it's the C in the ZFC, then every set has the same cardinality as that of some ordinal. So you can measure all cardinalities of ordinals. And that's a reformulation of the axiom of choice. Okay, so now we come to the continuum hypothesis. It begins with Cantor's theorem that if you look at the set of all natural numbers and the set of all real numbers, they do not have the same cardinality. Infinity does come in different sizes. And that's what you get out of the formal study. And then once you have that, the next question you would ask is there an intermediate infinity between the infinity of the natural numbers and the infinity of the real numbers? And the assertion that there is no intermediate infinity is the continuum hypothesis. The formula just says that if you have an infinite set of real numbers, either it can be matched with the natural numbers, it's countable, or it can be matched with all of the real numbers. No intermediate cardinality. And that's Cantor's continuum hypothesis. Okay, now I'm going to do something very, very dangerous, especially to a mixed audience, Wikipedia scholarship. Okay, continuum hypothesis, if you hold to the simple sets, that's obvious. From what I said, that's obvious. But it also holds for many not-so-simple sets. It's almost any set that you could find. Very hard to find a counter. So, what about the continuum hypothesis in mathematics? Well, in 1900, at the Second International Mathematical Congress, which I guess was held right nearby, Hilbert posed his now famous list of 23 questions to guide mathematics for the coming century. The problem with the continuum hypothesis was the first problem on this. In 1904, at the Third International Congress in Heidelberg, Koenig gave a lecture in which he claimed to solve CH. All parallel sessions of the Congress were canceled so that everyone could attend Koenig's lecture. The announcement was a sensation, widely reported by the press. I don't think that would happen now. The Grand Duke Frederick I of Prussia had Felix Klein explain the entire matter to him implicitly. The proof was wrong. So I don't know how that played out. Many others tried to solve the problem and also failed. So the problem of the continuum hypothesis quickly came to be widely regarded as one of the most important problems in all of modern mathematics. In 1940, that's the publication date, Gödel showed that it's consistent with the axioms of set theory that the continuum hypothesis holds. So you cannot refute the continuum hypothesis, assuming the consistency of the axioms. And then the real earthquake happened in 1963 on July 4th, when Cohen announced in a lecture at Berkeley that it's consistent that the continuum hypothesis be false. So you cannot prove it. And for those of you who are not familiar with holidays in the US, July 4th is a special day. Independence Day. I'm sure that's a coincidence. Or maybe not. I want to say a little bit about Cohen's method. So if M is a universe of set theory, then M contains blueprints for virtual universes which enlarge M. And these blueprints can be constructed and analyzed within the initial universe M. Now, if M is actually countable, so a mathematical structure, then every blueprint that you construct within M can be realized as a genuine enlargement of M. This was Cohen's discovery. He solved the extension problem. Cohen proved that every universe M contains a blueprint for an enlargement in which the continuum hypothesis is false. And that's how he showed that you couldn't prove the continuum hypothesis. In fact, the same method can be used to show that every universe contains a blueprint for an enlargement in which the continuum hypothesis is true. So you live in a universe of sets, and you see these blueprints for larger universes, maybe better universes. And in these larger universes, you can have the continuum hypothesis true, or you can have it false. So that's a problem. Now, Levy and Solovay showed in the late 60s that these enlargements preserve large cardinal axioms, if those axioms hold for a proper class. So if large cardinal axioms can help, it has to be in some unexpected way. So the dream that you'd resolve the continuum hypothesis by invoking a strong notion of infinity looks quite dubious. Now, what about the extent of Cohen's method? It is not just about CH. In the 50 years since Cohen discovered the method, which is called forcing, the technique has been vastly developed, and many problems have been shown to be solved. It's a serious challenge to the very conception of mathematical infinity. And the continuum hypothesis in that layered approach to the universe of sets is just a statement about V omega plus 2, which is way down at the bottom. Okay, maybe it's time to just give up. No, but large cardinal axioms are not provable. And that's by the Gödel second incompleteness theory. The large cardinal axioms are falsifiable. Okay, so I will make a prediction. No contradiction from the existence of infinitely many Woodin cardinals will be discovered within the next 1,000 years. Not by any means whatsoever. Maybe we encounter an extraterrestrial civilization that's been doing set theory for 5 billion years. You can ask them. No.
That's more than
what? Yeah, so I'm talking about the next 1,000 years. You're allowed to consult a civilization that's already been working for 5 billion years. Or maybe physics will hand us an NP-complete machine, and then you ask the machine. You're not going to find any inconsistency. So that's a prediction about the world, by the way. I've just made a prediction about this world for the next 1,000 years. Okay, is this a hint of a world beyond? Yes, I think. These truths cannot be proved. So this suggests that there is a component in the evolution of our understanding of mathematics which is not formal, which is not entirely based in proofs or calculation. All right, but how does one explain this? The skeptical assessment that the conception of the universe of sets is incoherent must be wrong. How else can you explain the predictions? No one has come up with another way of explaining the consistency of large cardinals except existence in the universe of sets. You can interpret the consistency, but that's a different issue. Okay, but if that's the only way to make these predictions, you must have a clear view of the universe of sets. In which case, CH must be true, or CH must be false. It makes no sense to say we justify large cardinals varied by their existence in the universe of sets, and say we will never know answers about the most basic questions about very small sets. That is incoherent. All right, so now we have a challenge. So let's go back to the problem of the continuum hypothesis. Well, what's the resolution? Well, perhaps one should begin by trying to more deeply understand CH. A natural conjecture is that one can more deeply understand CH by looking at a special case, or special cases. But which special cases? And does this even make sense? Well, now I'm going to talk about the projective sets in a slightly different incarnation. These are the simplest uncountable sets. So a subset of V omega plus 1, that's really what we're interested in for the continuum problem, is a projective set if it can be logically defined in the structure V omega plus 1. And that's a mathematical structure. It has one relation, the membership relation. And in mathematics, it's a standard thing, if you've identified a structure, to look at definability within that structure as a way of understanding the structure. Okay, and we can extend this definition to relations on V omega plus 1, a subset of the product, so a set of pairs from V omega plus 1 is a projective set if it can be logically defined as a binary relation in the same structure. So now we have a simple notion of subset of V omega plus 1, and we have a simple notion of function. So now we can localize the continuum problem. So first of all, let's recast the continuum hypothesis. It would talk about sets of reals, but it didn't have to. And this is the most natural formulation of the continuum hypothesis. If you have an infinite subset of V omega plus 1, then either it and V omega have the same cardinality, it's countable, or the set and V omega plus 1 have the same cardinality. That's just a reformulation of the continuum hypothesis, but it's more natural because it's pointing exactly to the sets of interest. So this is a statement about all subsets of V omega plus 1. But we want to look at a special case. So let's localize and formulate the projective continuum hypothesis. So suppose you have an infinite projective set, then the projective continuum hypothesis asserts either A and V omega have the same cardinality, or there's a bijection between V omega plus 1 and A, which is a projective set. So this is just a statement about the simple subsets of V omega plus 1. Now, I want to caution you, there are two moves here. One is, we're moving to simple sets and talking about cardinality, but we've restricted the functions we're looking at to witness cardinality. So it's not clear what the relationship is between the projective continuum hypothesis and the continuum hypothesis. But we don't care. We're just trying to understand the problem. Okay, now I should talk about the axiom of choice. So suppose you have a set of pairs, a subset of x cross y. A function from x to y is a choice function for A if for all A in x, if there is a B in y for which the pair AB belongs to the set A, then A f of A belongs to that set. The function is choosing. The axiom of choice is the axiom that asserts that every set has a choice function. Well, we're out. So what about the axiom of choice in mathematics? Hilbert's first problem implicitly had two parts. The first part asks whether the axiom of choice holds for all subsets of R cross R, and in a very strong form, for well ordering. It is the second part which asks whether the continuum hypothesis holds. Well, we can now localize the axiom of choice to the projective sets and formulate the projective axiom of choice. So if we have a subset of V omega plus 1 cross V omega plus 1, which is a projective set, we assert there is a choice function for it, which is also a projective set. So again, we're just localizing to the projective sets. So there were many attempts in the early 1900s to solve both the problem of the projective continuum hypothesis and the problem of the projective axiom of choice, achieving success for some of the simplest instances. However, by 1925, these problems both looked hopeless. They were hopeless. The actual constructions of Gödel and Cohen show that both problems are unsolvable. In Gödel's universe L, the projective axiom of choice holds and the projective continuum hypothesis holds. In the Cohen enlargement of L, as given by the actual blueprint which Cohen defined for the failure of CH, the projective axiom of choice is false, and the projective continuum hypothesis is also false. So the problems are unsolvable. And that's why the efforts in the early 1900s ran into a wall. In fact, when you analyze exactly the partial results you could have proved, they were able to prove essentially the best possible results. So this explains why the problems were so difficult. But the intuition that these problems are solvable was correct. And now we come to the unexpected. About 30 years ago, boy, it's hard to believe it was so long ago. Suppose there are infinitely many Woodin cardinals, then the projective continuum hypothesis holds. So why is this unexpected? You assert the existence of very large sets, and you're getting information about these very simple sets. That seems completely ridiculous. But that's what happened. And then about a year later, Martin and Steele showed from the same hypothesis that the projective axiom of choice holds. Now, I'm not stating the exact theorems, but restated them for this context. So, from the existence of very large sets, one solves those projective forms of both the axiom of choice and the continuum hypothesis. And the complete solution, I claim, is one of, and it's incredibly beautiful. So I would say we now have the correct conception of V omega plus 1 in the projective sets. This conception yields axioms for the projective sets. These determinacy axioms, in turn, are closely related and follow from large cardinal axioms. So the large cardinals are proving something else about the projective sets, these determinacy axioms, and it's those that give you the solution in quite a bit more. So, much as V omega is number theory, V omega plus 1 is second order number theory. It's a study of the integers with all sets of integers with plus and prime. So what's happened is we now have the correct axioms for second order number theory. And they're not obvious, but they're incredibly powerful. Well, what about V omega plus 2? We've handled V omega plus 1. If we could get the correct conception of V omega plus 2, we would answer CH. That's where CH lives. But we don't want to stop there. What about V itself? Okay, so what are we going to do? I want to go back to logical definability, and because I want to make a definition. So I want to introduce you to the definable power set. For every set X, P def of X, that's a definable power set of X, is the set of all subsets of X, such that Y is logically definable in the structure that X gives you, X with a membership relation, from parameters in X. P def of X is the collection of all, you might say, specifiable subsets of X versus the power set of X, which is the collection of all subsets of X. So to see the definable power set, you just look at X. To see the full power set, you have to step back in general and look at the ambient universe within which X lives. Now, the collection of projective sets, as I defined it, is exactly the definable power set of V omega plus 1. Okay, so remember, we had the cumulative hierarchy of sets, where we iterated the power set operation, and that gave us all sets. But now we have a restricted power set operation. What happens if we iterate that? Well, that's what Gödel did in defining L. So Gödel's constructible universe L. You define L alpha by induction on alpha. You start the same way as V alpha. L0 is the empty set. But at a successor step, you don't take the full power set, you just take the definable power set. And at limit stages, you just collect. And then what we've defined is a class of sets, and that's called L. Now, in the cumulative case, we know every set belongs to a V alpha. That's a consequence of the axioms. In this case, we don't know. But it gives us a new axiom. So that's the axiom V is equal to L. Suppose X is a set, this is what the axiom asserts, then X belongs to L. That iterating the definable power set, we reach all sets. That's the axiom. And what Gödel showed is that if you assume this axiom, then the continuum hypothesis holds. That's how he showed that you could not refute the continuum hypothesis. Mathematically, what Gödel did is solve the substructure problem. Cohen solved the extension problem. Gödel solved the substructure problem. Well, how does forcing affect this? If you have a Cohen blueprint for V equals L, then the axiom V equals L holds and the blueprint is trivial. So if you adopt the axiom V equals L, you completely negate the ramifications of Cohen's method. Cohen's method is powerless to show things are unsolvable. Well, maybe we're done. Maybe this is the resolution. Well, obviously not, but why? So we have to go back to large cardinals. The axiom V equals L in large cardinals. Scott showed in 1961, and that's before Cohen's results, that if you assume V equals L, there are no measurable cardinals. In fact, there are no genuine large cardinals. More disturbing to me, if you assume V equals L, there are no Woodin cardinals. So there's a conclusion. The axiom V equals L is false. So we've been teased. We've been offered an axiom that seems to rescue us from independence by virtue of Cohen's method, but our founding principles of infinity demand that we reject that axiom. Well, a natural conjecture is that maybe the key is to generalize the construction of L by using large cardinals to expand the definable power set operation. Maybe the problem in L wasn't restricting the power set operation, but restricting it too much. But there's another way, which is based on simply using large cardinals to directly generalize the projective sets. So, by generalizing the projective sets, one obtains an axiom, V is ultimate L. Why ultimate L is kind of the ultimate version of L. But you don't have to know how to build it. You just are led to the axiom. Now, this axiom settles the continuum hypothesis and much more. The axiom sharpens the conception of V to the point of rendering Cohen's method completely powerless for showing that problems are unsolvable. So it retains that feature of L. And the formal statement is any Cohen blueprint for V as ultimate L must be trivial. So if you adopt the axiom V is equal to ultimate L, which is a quite specific axiom, forcing can no longer show things are independent in the context of that axiom. What the axiom does, and what the axiom V equals L does, is it binds the width of the universe to its height. The width is where CH lives. How wide is the universe of sets? The height is large cardinals. and these two are bound together. But is V equals ultimate L the missing axiom for V? In particular, is there a generalization of Scott's theorem for the axiom V is ultimate L? Maybe history is just going to repeat itself, and there's going to be a theorem that forces us to reject this axiom, just as the Scott's theorem forced us to reject V equals L. But there's an associated number theoretic conjecture, the ultimate L conjecture. Now, I'm being a little misleading, but I'm trying to make a point. When I say number theoretic conjecture, the first thing you think of, oh, the number theorists have been thinking about this. No, they haven't. But it's a statement, it's in fact an existential statement about finite sense. Okay, now, if you have an existential statement about integers, and you can state it in number theory if you want, our conception of the integers demands that it's either true or false. You might say, well, what if it's unsolvable? If you have an existential statement and you show it's unsolvable, the existential statement is false. Because if it held, it would be solvable. So, at a very basic level, this conjecture must be either true or false. We don't have to worry about unsolvability. Now, we may never know the answer, but it is either true or false. Now, what's the future? If this ultimate L conjecture is true, then the axiom V is ultimate L is arguably the key missing axiom for V. In particular, and this is the point, there's no generalization of Scott's theorem for the axiom V is ultimate L. That's the point of the ultimate L conjecture. It's just to rule that out. And it's amazing to think that one could even formulate a conjecture that would do it. But it's a compelling argument. But maybe the universe is not so kind. If the ultimate L conjecture is false, then the program to understand V by generalizing the success we had in understanding V omega plus 1 and the projective set fails. So, I'm not sure how this story will conclude, but I'm absolutely confident of one thing. It will be beautiful.